Hello, good morning, and welcome to the last day of this workshop. And the first talk in the morning is by Shiroman Prakash, who will be telling us about a fermionic tensor model in 2 - epsilon dimensions. Shiroman.
Okay, thanks to the organizers for inviting me. It was a very useful workshop. Here I'm going to talk about a fermionic tensor model in 2 - epsilon dimensions. Okay, so we'll just, first I'll just motivate and review the physics of tensor models, which people may already be familiar with. Then I'll describe the formal large N solution of a d-dimensional fermionic tensor model, which is based on our work with Rhythm Sinha. And then I'll describe some work in progress which allows you to study 1D tensor models at finite-N via a more explicit 2 - epsilon dimensional expansion. And I'll describe some of the physics one might expect from that. Okay, so the motivation is, okay, so the SYK model has attracted a great deal of attention recently as a possibly simple model of holography. One of the reasons SYK model is interesting is because you can solve it in the large N limit, and the reason it can be solved in the large N limit is because the Feynman diagrams are dominated by what are called melonic diagrams. So if you just are interested in asking what sort of, SYK model is also random, based on a random tensor. If you're just interested in asking, what sort of field theory without a random tensor would also give rise to diagrams which are dominated by melonic diagrams, then Witten and Klebanov, later in Tarnopolsky, showed that, well, tensor models which had been studied by a large community of people, including Garo and others, also are dominated by melonic diagrams, and in that sense are similar to the SYK model. Of course, it's not true that the full-fledged dynamics in the sense of the holographic tool is completely identical to SYK model, as pointed out by Shiraz's paper recently, and this paper by these guys, because there's a Hadron growth in large number. But from at least in some respects, in terms of calculationally, it is similar to the SYK model. Okay, sorry. Okay, so again, we now sort of know 3 different large N limits. There are vector models, which are fields with 1 index, and these give rise to large N limit in which the leading order diagrams can be explicitly summed. Okay, and their dynamics are similar to free field theories, and even in the case of interacting models, we now have candidates for their holographic tools, which are higher spin gauge theories. The second large N limit, which we're familiar with, are those of matrix models, which are based on fields with 2 indices. Okay, historically, those 2 indices were a joint 2 indices from a joint representation, but now we know there's examples of bifundamental theories with gauge theories, which have this large N limit. And in this case, the large N limit are planar diagrams, which in a genus expansion look like world sheets of the string, so they're closely related to string theory, but you cannot sum even all the leading order diagrams, and hence the dynamics is very non-trivial. In a few interesting cases, like N=4 super Yang-Mills and AVGM, we know that matrix models are dual to Einstein-like theories of gravity. And okay, the new sort of large N limit are these melonic tensor models, which are based on free fields with 3 or more indices. these give rise to a large N limit where all the leading diagrams can be explicitly summed, but in a sense, the dynamics is still non-trivial in the sense that scaling dimensions of operators and all change. And I guess we do not know much about its holographic dual, although Vasily have talked yesterday about possible holographic duals for free tensor models. It would also be interesting if one can drive duals for interacting models, which is the more important question. What we'll see is that actually this large N limit is slightly difficult to take. So although for 1D theories, this large N limit works fine. If you try to define a theory with D greater than 1, okay, there often are difficulties in defining such a theory, which we'll see in the talk. Okay, so one motivation for studying tensor models is, okay, we may be primarily interested in matrix models, but there could be indirect relations between tensor models and matrix models, like there are between vector models and matrix models. So just to review the relation between vector models and matrix models. Okay, before ABJM, the matrix models people constructed were typically based on a joint representation, so there wasn't an obvious connection, but ABJM theory is based on bifundamental fermions, which would be, or bifundamental matter, which is UN cross UN. The second N can be changed to an M. Okay, the second N can be changed to an M, and you get ABJ theory, and when M over N is small, the theory is a vector model, and the theory can in principle be solved, and there's a higher spin dual proposed. When M over N corrections are taken into account, more and more planar diagrams are included. At any finite order in M over N, you can in principle sum all these diagrams and the theory can be solved. But when M over N is any number order 1, you would need to include all planar diagrams and the theory can't be solved. So there's at least a sort of a parameter that if you do perturbation theory in this parameter, you can go from the vector model large N limit to the matrix model large N limit. Yeah, so in principle, it's all classical along this whole line, even though we can't actually sum all the diagrams. We can also understand this in terms of the operator content. When M over N is small, the spectrum of single trace primary operators is very small. So essentially, there's order 1 operator for each spin S. And because there's so few single trace primary operators, you can show via simple argument from conformal representation theory that all the scaling dimensions are protected. So even in a strongly interacting limit, most of the scaling dimensions would be the same as in free theory. When M over N corrections are taken into account, you would have, mixing between operators that were previously considered double trace or triple trace as you increase the powers of M over N. And when M over N is order 1, there's a large number of single trace primary operators, which are strings of matrices of the form trace AB, AB, etc. And now the number of primary operators is, they look like different closed string states. And because there's a large number of single trace primary operators, their anomalous dimensions are not protected. And there's a possibility that, say, the anomalous dimensions of higher spin currents diverge at strong coupling, giving rise to a holographic dual. Okay, so this is the connection between vector models and matrix models. And just to summarize it in a picture, which it can only be made really precise in a particular supersymmetric case of ABJ to ABJM, where on one hand you have these two field theories which are just stated by a simple parameter M over N, and in the dual picture, we have a higher spin gauge theory, except with Chan pattern factors on each of the fields, I equals 1 to m. And in this picture, since 1 over n is the gravitational interaction, m over n is like a gravitational Tooft coupling. And somehow when this gravitational Tooft coupling increases, these fields, say, undergo a confinement transition and have to become type 2a supergravity on ADS 4. Yeah. Well, I don't know this line has no obstruction. I only know these corners.
That's right.
And so, I mean, we would, we'll see. We'll see in the end a simpler, non-supersymmetric example where there is an obstruction in the middle. Okay, but here, I mean, of course, the free theory can be described for any m over n. Okay, and weak interactions can be done for m over n. Yeah, could there be something interesting that happens in between here? We really don't know. So this is just this is a vague picture that needs to be clarified, and that's part of the motivation. Yes. So we don't know that there's a phase transition in between.
Hello. Hi, Shiroman here. I was just wondering, maybe it's not very well posed, but could there be an intermediate regime, let's say, where m scales like square root n or something like that, in which, of course, m over n is small, but at the same time, the whole thing scales like n to the 3/2, and there is maybe a non-trivial limit, and m over n is like 1 over root n, so you can in principle sum it up. Is there something like that, do you think?
Right, that's an interesting question. I've thought of doing something like that for this tensor model, but I've not tried it for just for these. So I don't think that's been looked at. It's a good. For m order n to the power x, presumably there's some x range of x for which you can sum the diagrams. It's a subleading and. Okay, so these are sort of these are the sort of open questions with matrix models, and that's actually an interesting idea. Okay, but so this is the connection between vector models and matrix models, which is still needs to be fleshed out more. But we have this other large n limit called tensor models, and how do these fit in this picture? I won't. Give a very complete answer to the question, how do they fit into the picture? I mean, I'll put some obvious conjectures at the end, but this is perhaps the motivation to study tensor models, even though they have a weird holographic tool, just because the hope is you can approach the matrix model from a few different directions, not just m over n. Okay, so that's ultimately this is all motivation. Yeah. Okay, so what exactly are tensor models? So we can consider fields with 3 indices. Okay, and these are defined by Gros and others, A, B, C. Okay, let's take the 3 indices, for instance, to transform in the representation UN cross OD cross UM. This OD sort of, well, it looks like transverse directions. Some people like to call this D, but just 3 numbers, maybe all 3 you can take to be N. Though, even if they're different, the melonic dominance comes in automatically if they're all order N. Okay, and when you draw these diagrams, it's convenient to, we can also take ON, OD cross OM, but if you want fermions, the 3 cannot all be U. Okay. So then when we draw Feynman diagrams, we'd use like a Tooft double line notation, but with 3 lines for each of the 3 groups. And then, say, orange loops would give you a factor of n, blue loops give you a factor of d, and yellow loops give you a factor of m. Okay. or whatever the three colors you choose. Okay, so to get melonic dominance, you have to we consider these fermions with a particular four-fermion interaction called a tetrahedron coupling. Okay, that coupling can be seen from this picture. So, the first index contracts with this guy, the second index contracts here, and the third index contracts here, and the same is true for all of them. So it's like, so the indices are contracted over, the red line goes here, the blue line goes straight, and the green line goes here, and this gives rise to a vertex which, when you draw it in some other representation, looks like a tetrahedron. Okay, using graph theory or just by drawing some diagrams and convincing yourself, you can convince yourself that the natural 't Hooft limit is g squared ndm held fixed, or g, if you keep them all equal, that's g n to the 3/2. This is because you get n cubed or ndm from these three lines and two g's. So for the finite self-energy corrections, you need to have this 't Hooft coupling held fixed. Okay, and then you ask what are the corrections to this diagrams that are leading order in n, and they're just, this looks a bit like a melon, and you can imagine cutting these lines with circles further and further, and those are the only diagrams which contribute. So they're a subset of planar diagrams, which we call melonic. Okay, it's a richer subset than the subset of diagrams which contribute for vector models, but it's still summable. Okay, so Klebanov and Tarnopolsky solved this model, and they found they found the fermion scaling dimension, and the spectrum of fermion bilinears was identical to that of the SYK model. Of course, as mentioned earlier, because of these three indices, you can find a huge number of gauge invariant single trace operators. These would be as many as you have diagrams in, say, phi cubed theory, okay, which is exponentially large, and this means the holographic dual is quite different from SYK. And there's Hagedorn growth, etc. Okay, but at the level of just spectrum of two-point functions or scaling dimension, the two-point function or scaling dimension of fermion bilinears, the results are identical. So it's similar to SYK in that sense. Okay, and we'll see how it was solved when I study the higher dimensional generalization. Okay, so now if you want to generalize this to higher dimensions, the most natural generalization is to consider a bosonic model. This is because a phi to the 4 theory will be relevant in d less than or equal to 4. So you can study this in, say, 3 or 2 dimensions. And this is the bosonic tensor model where the phi 4 theory, instead of being the usual indices, say, of the vector model, are contracted via each phi field has 3 indices, and they're contracted via that tetrahedral interaction. So this interaction actually is not positive definite because it's not the square of something. Right? It's not phi I, phi I, phi I, phi I. So there's a negative direction. So this it's not completely well defined, but okay, it can still be studied formally in perturbation theory, like phi cube theory in 6 dimensions. So when solving this theory in less than 4 dimensions, they found that unfortunately the theory is not well defined, and the reason it's not well defined is one obtains a complex scaling dimension for the lowest mass bilinear, I5 phi phi. Okay, and this complex scaling dimensions of the form d by 2 plus I times a number, and you can show that maps to a field with a mass below the EF bound. So one could interpret it as saying that the large n saddle point is unstable. Or you could just simply say that, okay, the large n fixed point doesn't exist. Okay.
Shiroman?
Yeah.
Is this model renormalizable in the sense that, like when you do it in higher dimensions, you don't generate any new?
This model, the Bosonic model, is renormalized in T less than 4 dimensions.
Okay, so you don't generate any new kind of 5-4 coupling?
You do generate them. So if you want, so they also, so in fact, the renormalization of this, a general 5-4 coupling, the beta function was computed by Mack and Osborne many years ago, and they're using those results. They look at the normalization. So you do have, so in the large N limit, this is sort of all that's dominant from melodic diagrams. So if you just want to write the formal large N solution, you keep just this coupling. But to renormalize it, you have to add additional couplings.
So in addition, how many couplings?
You can restrict to 3, total 3, including this. But the vertices have a few different forms. So I'll actually mention these later, how it's renormalized carefully. Okay. Okay, so what we do is, yeah.
Other couplings consistent with the UN times OD times
Yeah, there are
UN?
other couplings. And if you want to renormalize it, you write down the most general set of couplings. And you'll see that this generates those couplings, whereas those don't generate this coupling. And we can explicitly show, they can explicitly show that there's no solution to a fixed point in 4 minus epsilon dimensions. There's no real solution. The solution is imaginary. It has one of the couplings being complex, if you wish. Okay, so this, at first you would find this just by doing solving these large N Stringer-Dyson equations, which I'll describe, and then you can do a more precise finite N renormalization, or even a large N renormalization, and see that there's no fixed point. Okay, and yeah.
Is the solution of a 1-loop beta function, or you can?
You have to do at least 2 loops because the nature of the diagrams.
Okay, but they're all melodic. So you.
No. Well, you have a finite N beta function.
Okay.
And then you give all the couplings a natural scaling, and you drop subleading terms. So you have the full finite N beta function. So you could ask, are there fixed points maybe with just weird different scalings as well from such a finite N beta function, which is again the motivation for looking at a finite N beta function. So yeah, so that is they just do finite N beta function, and then you can put in the natural scalings and drop subleading terms. Oh, yeah. Okay, and again, that's a RG type of thing. So perhaps, okay, although this, so what we do is we consider a d-dimensional generalization of this model, but sticking to fermions. Okay. Okay, one motivation is, unlike the Bosonic model, it doesn't have a negative direction. But the main reason is then we can discuss. Okay, so this is what we study the most. Just take the fermionic model and generalize it to d dimensions. In higher than 1 dimension, there are two different couplings you can write down from the gamma matrix algebra. So it's a bit more complicated, and we can ask whether you will get complex scaling dimensions in higher dimensions here or not. Okay. So of course, in the large N limit with these two couplings scaling appropriately, the theory is also dominated by melodic diagrams, which can be explicitly summed for arbitrary t. You can, if you were to take the lambda equals infinity limit just naively, if t is less than 2, this defines an infrared fixed point, which is sensible and okay to do. t less than 2, t equals 2, we won't discuss. When t is greater than 2, of course, the theory is not renormalizable at finite n. But of course, if you just keep the large n diagrams, there's no divergence. So it can still be used. Yeah, you could conceivably use it to define a formal UV fixed point in large n. We'll see these. Okay, well, though there's many problems with doing this. Just one reason you might consider it is because the vectorial Gross-Nouveau model, defines a fixed point in t equals 3 even at finite n. Okay, and you can and of course the reason really it's well defined is it's the IR limit of a Gross-Nouveau Yukawa model in 4 minus epsilon dimensions. But it can also be studied using the Gross-Nouveau model in 2 plus epsilon. Okay, so it's not like it's never. So perhaps for d equals 3, you could define a melonic Gross-Nouveau model, though we'll see it also has a complex fixed point. Okay, and the large n solution goes the same way as any SYK type calculation. So first you try to find the exact propagator. It's a free propagator plus this melonic correction, and then again you can cycle the melonic, you can repeat the melonic corrections here and inside and inside. In the strong coupling limit, you just drop the free term and you have a self-consistent scaling solution. Okay, which you can just explicitly solve using dimensional regularization in d dimensions. Okay, and you find the fermion has mass dimension d over 4 in the strong coupling fixed point. Okay, so once you have the exact 2-point function, the next thing you can calculate is the spectrum of single trace bilinear primary operators with spin 0, because in one, or you could also do higher spin, but we'll just do spin 0. So these are operators of the following schematic form: psi bar d slash to the n psi. Okay, I like to. It's necessary to divide these into 2 different categories. If n is odd, this would be a parity even scalar in t equals 3. So there's parity even scalar bilinears, and if n is even, it's a parity odd scalar. Okay, in d equals 3. So there are 2 different types of spin 0 operators, and the way we'll calculate their scaling dimensions is as follows. So we imagine calculating the 3-point function psi bar psi with the bilinear operator in keeping all melonic diagrams. So that's represented by this shaded 3 guy, and you can convince yourself it follows equation that looks schematically like this, except this should be the free 3-point function here. Okay, so it obeys a Schwinger-Tyson equation, and in the strong coupling limit, you would hope you'd assume you can drop the first term. So that means acting on the exact 3-point function with this sort of one rung of with this ladder diagram, or what I'll call integration kernel, should give you back the same 3-point function. Okay, so the exact 3-point function should be an eigenvalue of this ladder operator with an eigenvector of this ladder operator with eigenvalue 1, and that's represented by this eigenvalue equation. Okay, and of course the form of the 3-point function depends on the scaling dimension of the operator. So we'll find that this 3-point any conformally invariant 3-point function will be an eigenvector of this integration kernel, but the eigenvalue will only be 1 for certain values of the scaling dimension, and these are the allowed scaling dimensions. Okay, this is the expression for the integration kernel. Okay, and these are the allowed forms for the parity even and parity odd 3-point functions, and they depend on tau, which is the scaling dimension scaling dimension of the scalar. Okay, and the claim is this 3-point function will be an eigenvector of the integration kernel in general, but for some values of tau, it'll have eigenvalue 1, and those are the allowed scaling dimensions. Okay, and acting on these kernels, we find an explicit expression for the eigenvalue for each case. So the task is just to solve, for what values of tau is this expression equal to 1? Those are the allowed scaling dimensions. Okay, any questions on this? So, okay, it's hard to do this analytically, so you just do this numerically. So let's first look at d equals 3, or any d. So the blue curve is the is g of tau, and the orange line is 1. So at the intersections where g of tau equals 1, so say this is 3 point something, close to 4, and this is maybe 5.4. These are the allowed scaling dimensions of operators. So this is how you determine the spectrum of operators. And you'll get an infinite tower of operators, parity even and parity odd operators, and you expect, for example, for the odd operators, you expect their scaling dimensions to be 2n plus d by 2 if it was just a free theory, where because d by 2 is the scaling dimension of the fermions, and 2n would be from the derivatives, but there'll be some amount larger than that from interactions, delta n. Okay. And of course, we're interested mainly in the case less than 2, but I just gave a plot for d equals 3. So in d equals 3, you find scaling dimensions 3.69, 5.53, 7.51, etc. These approach 2n plus 1.5 as expected. But you don't find an operator for n equals 1, n equals 0, okay, which would be just the lowest operator. And this instead, corresponds to a complex eigenvalue, a complex value of scaling dimension, which is 1.5 plus 1.79. Okay, so this is the same form found in the Bosonic model, and it again suggests the fixed point doesn't exist, or if there was a holographic tool, it would have a field below the BF bound. Okay, so it turns out that again the d equals 3 theory also has a complex mode just like the Bosonic theory in d equals 3. Although other than that, it seems to be sensible. I mean, as sensible as the d equals 3 Bosonic theory. Okay, you can study the spectrum just in general dimensions and see where do you find real and complex spectrums. Okay, so one can check numerically that for any d less than 2, we get a completely real spectrum and there's no complex mode. Whereas once you increase d slightly above 2, because this guy flips, there's always generically a complex mode. Okay. Okay, this is a little different from the Bosonic model, because here not only in d less than 2 is it an infrared fixed point, but you also get a real spectrum. Whereas the Bosonic model, even though when you have d less than 4, you get a complex scalar. So it's a qualitative difference. But there's a real eigenvalue for any d less than 2. You can also search for higher d, and you find in general near d equals 2 plus 4n, there's a window with a real spectrum. Okay, which, for example, near d equals 6, there's a window with a real spectrum. I don't think that there's any physical interpretation to this, but I mean, if you're naive, well, originally you might have thought with n cubed degrees of freedom and 5 branes, there's some 60. Maybe tensor models are related to M5 branes, and it's true you get a real spectrum near d equals 6, but I don't have anything concrete to say about it, and this is just the spectrum near d equals 6. In 2 and 6, it's, well, in 2, you can ask about mass generation, but so in 2 minus epsilon, when epsilon is very small, it's almost free theory. The spectrum approaches the free theory as epsilon goes to 0. And in 6 plus epsilon, it also approaches the free theory, although the scaling dimension of the fermions is different. Okay. So it looks a bit like a free theory. So this is the spectrum. You can also solve these. So as I said, because the theory looks free near g equals 2 and 6, you can solve this. You can solve for the same equation g equals 1, just perturbatively in epsilon around d equals 2. This is still a large N calculation. It's just solving the saddle point, not numerically, but as a power series in epsilon. Okay, and this is so this is what the spectrum of the 2 minus epsilon dimensional theory looks like to the first few powers in epsilon. Notice that, okay, there's this symmetry between shadow operators and non-shadow operators. So this minus is just the shadow of the plus operator and shouldn't be taken too seriously. But these are the spectrum, and we can see that it's real when epsilon is positive and imaginary when epsilon is negative. So you can confirm the numerical findings this way.
Sorry, this is the scaling dimension at what coupling?
No, there's this one fixed point, which is the strong coupling fixed point.
Okay, so you solve for the beta functions and then
No, this is just what I described before. So in this, just like in SYK, if you assume a consistent strong coupling solution that's dominated by Bosonic diagrams, then these have to be the scaling dimensions.
Take it to be infinite coupling, or
There's infinite coupling lambda in that picture. Okay, I mean, when you renormalize it, you'll find a coupling of order epsilon at the fixed point. But in this large N picture, it's just going to the strong coupling limit is how you define the conformal fixed point. Okay, we'll later discuss the renormalization briefly in the next. And that's what is more interesting. So, but this is the spectrum, and we can see just that it's real and imaginary in some when epsilon is positive or negative. And this is the spectrum of parity even operators. Okay. We can also do this in 6 dimensions, and you see when epsilon is positive, it's real. It's likely the 6D theory is not consistent, but maybe one can also have expressions for the higher spin spectrum, at least check to what extent those are consistent with strap expectations or something.
So maybe you'll say this later, but the coupling at order epsilon is order square root epsilon.
Square root epsilon. The tetrahedral coupling comes out to be order square root epsilon. This is why you have to go to 2 loops in the beta function in 2 minus epsilon dimensions, or 4 minus epsilon. Okay, so these large N results suggest that there is weakly interacting in t equals 2 minus epsilon, and also that the spectrum is real for epsilon goes from all the way to 1. So it seems like a natural thing to develop an epsilon expansion to study the 1D tensor model at finite-N. And this would be analogous to the 4 minus epsilon expansion for the Wilson fixer fixed point. Or for the Gross-Neuer fixed point starting from 4 minus epsilon dimensions. This requires carefully renormalizing the theory in 2 minus epsilon dimensions and solving for fixed points of the beta function. Of course, there could be subtleties in interpreting results because the 1D theory is not strictly conform. But we're just proceeding naively the same way you would do for the Wilson fixture. Okay, so you need to write down the most general renormalizable action involving these indexed fields. Okay, so to renormalize the tensor model, you need three different types of four fermion interactions. These are tetrahedron interactions, pillow interactions, and vector interactions. Okay, and I'll show you what these look like in the next slide. And combined with the different ways of contracting spin indices, you can get various interaction terms, although you can also impose symmetries to make some of these equal. Okay, but there's three different types of four field interactions that you would get when you renormalize a tensor model. Okay, so the first are the tetrahedral interactions, and this is how the index is. Okay, so these two are different color. One is green, one is orange, but it looks orange. But there's so here this is the tetrahedral interaction, and this is how the colored index lines look. So it's okay, and well, there's two of them because of the different gamma matrix contractions. Pillow interactions, you have two fields. I mean, two indices are contracted to one of the fields, and one is contracted to the other field. So the diagram looks a bit simpler. It looks like this. The pillow interaction would arise, for instance, if you had a gauge field, and you were to integrate out the gauge field. So the gauge field would have two lines of the same color. And when you integrate it out, you would just get this sort of four fermion interaction, which looks like this. Okay, so you have to add various pillow and because in a different way of looking at it, the tensor model guys call this a pillow interaction. Okay, so you have to add pillow interactions, and finally you would add what's called a double sum interaction or a vector interaction, which is just the vector model interaction, but 3 lines instead of 1. So if all the 3 indices contract to the same field, then it's just a vector model, large N limit, except N cube instead of N. Okay, so these are the 3 types of interactions that one needs if you want to renormalize a general tensor model. Okay, and in the large N limit, there's this sort of hierarchy of interactions. So vector interactions only generate vector interactions. So you don't need to, that's why you can just consider the vector ON vector model or the Gross-Niver model. If you add pillow interactions and you use the standard large N scaling, then pillow interactions only generate vector interactions or other pillow interactions. So you could just stop here and define a large N limit with vector and pillow interactions, although it's not a very interesting large N limit. And finally, if you include tetrahedron interactions, then this will also tetrahedrons generate pillows and vectors. So tetrahedron. So in that sense, there's this hierarchy. So to renormalize the tetrahedron interaction, you need these 2. But if you want to renormalize just these 2, you don't need the tetrahedron. Okay, and this is just a picture showing how does a tetrahedron generate a pillow. So in this one loop diagram, you see 2 tetrahedron vertices, and when you follow the lines, you get a pillow. Okay, a pillow interaction. Okay, so the blue line comes here. And just combining pillow interactions, you can see, okay, they also generate other pillow interactions because, as shown this way, the blue line comes here, this line, and okay, and they can also generate vector interactions. But the diagrams where they generate tetrahedrons are suppressed by 1 over N. Okay. So anyway, so then you have these different interactions, and you can write down the beta function for them, and it schematically looks like this form. So because the tetrahedron is not generated by pillow and tensors, it has just here, and then the pillow diagram has contributions from the tetrahedron and the pillow, and this beta function here has so you get a coupled system of finite-N beta functions. This calculation is almost finished, but it's not completely finished, so I'm not going to be able to report the results of the 2 minus epsilon beta function. But the conjecture is which seems to be supported, is that for d less than 2, you will find a purely real fixed point. The tetrahedral coupling has to be order epsilon to the 1/2, which means you need to go to 2 loop corrections to the vertices, and not a 1 loop vertex correction to calculate the beta function. Okay? So although the work is in progress, the beta function for the Bosonic tensor model in 4 minus epsilon dimensions is already done. So I'll just tell you what the results are there and how we expect differences in the 2 minus epsilon Fermionic tensor model. Okay, so as I said earlier, the Giombi, Klebanov, and Tarnopolsky studied the melonic phi-4 theory in 4 minus epsilon dimensions. And they found that there's a complex dimension for t less than 4, unlike in our case where there's a real spectrum for t less than 2. The most general beta the beta function for the most general I to the 4 interaction was calculated in the index notation by Mack and Osborne in the 90s, so you could just use that existing calculation to read off the beta function. And this is what, once you use it, this is what it looks like. So I'm just writing the beta function for the tetrahedron and the pillow here. Okay, this is fairly complicated, but if you scale the guys in the natural large N scaling and just keep the leading order terms in the large N limit, we find the following system of 3 equations where the tetrahedral, the pillow, and double trace coupling. Okay, and if you look for a solution to these equations when G is when the tetrahedral coupling is non-zero in 4 minus epsilon dimensions, you find that G is square root of epsilon by 2. The pillow interaction, and here by symmetry you can combine all the pillow interactions into just one coupling. The pillow interaction comes out to be complex 3i, and so does the vector interaction. So the idea is turning on a fixed point, in short, requiring that the tetrahedral interaction is non-zero at the fixed point means that there's no real fixed point for the pillow and vector interaction. So this is the sense in which there isn't a tetrahedral fixed point at least in 4 minus epsilon dimensions. You could ask, say we studied ON cross OT cross OM tensor model with these ratios fixed. Maybe these numbers would change and you could get a real fixed point for some value, but in fact, the numbers stay exactly the same. And you just define G's a little differently and there's still a complex fixed point. Okay, and in contrast, for the fermionic model, we'll have similar expressions, but the expectation from the large N calculation is that you'll get a real fixed point in 2 minus epsilon. Okay, so you can ask, is this absence of a real fixed point really a special feature of tensor models? So I said tensor models are ugly, but maybe they're not ugly. Okay, so a simpler model you can consider, which is a natural model, is phi-4 theory with scalars in the bifundamental representation. So not adjoint, but two indices n and m. Okay, so this is a bifundamental phi-4 theory. Okay, and when m equals 1, this is a vector model, and we know it has a well-defined large N fixed point in 3 dimensions, or even at finite N. Okay, but let's study its renormalization in general, and the expressions by Mack and Osborne from the 90s allow you to get the results, and also Klebanov and Osborne and Seju, in fact, studied this some time ago. But I'll tell you what the results are. So here you just need 2 different types of interactions. There's a single trace interaction, which is like trace phi transpose, phi transpose, and a double trace interaction, which is trace of phi phi, trace of phi phi. Okay, so this is the most general renormalizable action for this two-index model. Okay, and there's a natural large N scaling where the single trace guy goes as well, G1N is G1 tilde and G2N squared is G2 tilde squared. Okay, this is the natural 't Hooft limit for such a model. So we can ask, what does the beta function look like? In this case, and well, you calculate the beta function and you find the fixed point. You find there's a real, if you require there to be a real fixed point for this single trace, if you require this single trace coupling to be non-zero, you find a fixed point where G1 is epsilon by 4. But then the double trace fixed point comes out to be complex. Okay, so in fact, even for this pi-fundamental critical phi-4 theory, with both ranks equal m and n, there exists no real fixed point. Okay, and here, of course, the dimensions are completely positive. It's a more familiar interaction, so it has nothing to do really with the tetrahedron. It's just okay. Okay, so this is for m equals n. So this is n bifundamental with both equal. We know that for when m equals 1, there is a real fixed point. It's the usual ON vector model. So presumably there's a transition in between. So if you calculate the beta function, keeping with for OM cross ON model, keeping m over n fixed, and that's alpha. This is what the equation looks like. So here the coefficients depend on alpha. So solving for a real fixed point where G1 is non-zero, it turns out it's only possible when alpha is less than this number, or 1 over alpha is bigger than this number, which is 0.1. Okay, so there is a real fixed point, but as you increase m over n from 0 to 0.1, somehow it becomes complex.
Minus epsilon?
No, this is all 4 minus epsilon equal 5.
This is 4 minus epsilon.
We hope to do similar calculations in 2 plus epsilon or 2 minus epsilon for fermions.
1.
This bound is just, so looking here, you see that, I just keep the two, you can ask, is the leading order solution real as a function of epsilon? I don't have to plug in epsilon equals 1. I'm just asking, in the epsilon expansion, is the first, okay, GT is going to be, G1, G2 will be proportional to, it could be proportional to square root epsilon, or it could be, to solve this, you ultimately have, just to solve at second order in epsilon, or you'll have to solve a quadratic equation.
Sorry, I'm kind of confused. So when m is 1 in this previous model,
in this previous model,
m equal to n, okay.
Yeah.
So you had complex.
Yeah, it's complex. Just I don't have to plug in any value for epsilon. Just the leading order correction in the epsilon expansion is complex.
So the statement is that when m is less than something in n, then you get a real this complex guy goes away.
Well, when m is 1, it's the critical ON model, which we know has a real fixed point.
Okay.
Okay, and when m is n, it's a complex fixed point. So now you expect there's some value in between for m over n, which is the largest value. You expect a transition as you increase m over n, and then I'll tell you what the transition is.
Okay.
Okay, so maybe I could have put a few more equations, but if you, so these are the beta functions. So you assume G1 is non-zero, and you solve for what G1 is as a function of alpha, then you plug it back in here, and you solve for G2. You'll get a quadratic equation. That quadratic equation could have either two complex solutions or 2 real solutions. We find, and whether it's real or complex depends on the parameter m over n. We find it's real when m over n is less than 0.1. And complex when m over n is greater than 0.1. Okay, so this is, Yeah, this is a case where one can do m over n, or finite m over n, because you're instead doing epsilon expansion to get weak coupling.
I mean, this is probably slightly off field, but this is should I understand this statement as some kind of a statement about cosmological constant problem in Vasilev theory? Or what is the...
Yeah, so I mean, it would be interesting to understand it in terms of Vasilev theory. But here, as a calculation, it's a simple calculation to do. Okay, and it means, so we're almost finished the talk. So it means, what does it mean? Well, it could mean different things, but okay, so this is, it means, in the appropriate Vasiliev theory that something happens when the 't Hooft coupling becomes 0.1. The theory breaks down. Okay, which is what you would expect, because you could ask the question, this is a large N matrix model which is strongly interacting. It could have a simple non-supersymmetric holographic dual. You could have this ABJ story go on, and what happens? And here, unfortunately, M over N breaks down at a finite value. Could be at that value. It's gravity theory. I don't know. Okay, but so let me just say that exact same thing slower for everyone. So again, recall the picture for ABJ M. So when ABJ is M much less than N, it's a vector model with Chant pattern factors. I equals 1 through. Okay, and when M over N increases, it's ABJM theory, which is dual to Einstein gravity, subject to, okay, so M over N in this picture is a gravitational 't Hooft coupling for the Vasiliev theory. So, and we don't know what happens in between, but somehow, if nothing happens in between, as you increase the 't Hooft coupling, somehow these fields combine. If something happens in between, we don't know. Okay, but of course, what role does supersymmetry play in this diagram? Okay, so for n equals 4, super Yang-Mills, it's conformal because, as Shiraz and others we pointed out, was that it's conformal because of supersymmetry. But ABJM is conformal because in Chern-Simons theory, K is an integer, so it cannot run by quantum mechanics, and all the other couplings are related to K by supersymmetry. But you could just as well have a theory, a non-supersymmetric theory when K is without any supersymmetry, just a UN cross, just a bifundamental Chern-Simons theory at fixed K, coupled to fermions, and there's no marginal coupling, so it's in fact a consistent conformal field theory which looks just like ABJM, and we know when M much less than N, it has a Vasiliev higher spin dual. So you could increase M over N and here increase the gravitational coupling and ask what happens. Okay, and I've talked about this before, and it was part of the motivation for the original vector model paper, which these people worked on. Okay, it is a difficult question to answer, but you could ask an easier question. Say, I consider the critical ON model a bifundamental version. It's dual to a higher spin gauge theory, maybe with Chant pattern factors. As you increase M over N, you get that bifundamental critical ON theory. So in the dual picture, there's a gravitational 't Hooft coupling being increased, and we see that 't Hooft coupling can't get too strong because otherwise the CFT ceases to exist. Okay, so that's easier question. As of course, the 5-4 theory is different from the non-SUSY bifundamental gauge theory because, for instance, anomalous dimensions don't grow as log S in this theory. So it's not quite asking the more general question, is there a non-supersymmetric dual? But this toy model for a non-supersymmetric holographic dual seems to have problems. We hope to answer the same question for the 3D Gross-Mill model with calculations in progress. Okay. If you were to generalize it slightly to ON cross OM with D order 1 and M over N large, as D increases, we expect, I have to confirm this by some calculation, that M over N, the critical value of M over N would decrease. And once D is order N, it returns to the melonic regime. So it suggests that, you can also define a which is obvious. I guess you could define a 1 over D expansion to take the Bosonic limit to a matrix. Okay, and okay, the other obvious expansion you can do is between vector and Bosonic tensor model. So this is this sort of, well, an obvious relation between these three models, but one can explore how useful it is if you have an epsilon expansion, where you have an explicit finite-N solution. Okay, and so that's it. Really, okay, I mean, I should end, but okay, you can also ask, is there a one-dimensional fermionic matrix model? That could be studied by several ways. It could be studied from the Bosonic tensor model in a 1 over D expansion, from a vector model in an M over N expansion, and in 2 minus epsilon dimensions via the beta function. You know, unfortunately, you could also just directly solve it because it's a quantum mechanics model, and Klebanov and collaborators solved it for, at least for D equals 1, like just UN cross UN matrix quantum mechanics using some clever techniques. And they find, of course, you can solve it, and it's a sensible quantum mechanics theory, but they claim there's a finite gap between the ground state and the first excited state, even in the standard of large N limit. So it doesn't give rise to conformal quantum mechanics. Okay, but you know, you could study this for larger values of D where they couldn't solve it exactly, or for D scaling as a power of N. And this is what we hope to do with the epsilon expansion. Okay, so maybe I will end here. I mean, one conclusion is that it's difficult to construct theories with Bosonic dominance in higher dimensions. There's a supersymmetric model which I didn't discuss. Of course, to complete this question of are there higher D Bosonic theories, there are a variety of other models you can construct, say with both bosons and fermions. They're not supersymmetric, and you can check if they have real fixed points, and that should be done. So you probably will not get a real fixed point, and yeah, and that's the end. So thanks.
So the anomalous dimensions you computed in the epsilon expansion for these operators which look like psi bar delta to the power 2 and psi. If you look instead at operators, composite operators which are like psi bar psi to the power k, then
single trace or composite.
Yeah. So
double trace.
So just like psi bar psi to the power k, like many say.
A double trace operator, or multiple trace operator.
Multiple trace. So do you still get like for psi bar psi, for the lowest thing you got a complex scaling dimension, but for these class of operators, would you still get these things in epsilon?
I haven't. I guess if you put enough derivatives in between, you should get a complex scaling dimension, twice the complex scaling dimension.
No. So I'm not talking about derivatives. Just if you.
But just the actual one. I mean, I've not calculated those scaling dimensions, but. Psi by psi has complex. So I presume psi by psi would. No. Well, they would factor. Yeah. So the 1 over n would be whether the 1 over n correction is complex. That's true. It would factorize. Yeah. Of course, the single trace psi by psi. Sorry, I thought it'll have a real dimension probably actually, because that's the double trace guy.
So I thought you were doing fine. You showed some finite-N results, right? The anomalous dimension.
Well. These are large N results. Okay. You want to know? I mean, finite N. We solve the beta function and find a complex solution. I didn't write the scaling dimensions at finite N.
Oh, I see. Okay. I didn't realize that.
In principle, those can be reproduced. So that's.
I just had one more question about this bifundamental scalar theory. So there is a particular m over n where it becomes this thing. So at that m over n, how much anomalous dimension you can get for the, say, high spin currents? Do you have a...
Well, one can calculate it in the epsilon expansion, which might not be useful. One can also calculate it by order in M over N.
Because M over N is 0.1, maybe it's
yes, not... So in fact, we have... there's a 1 over n squared calculation of the higher spin spectrum, which can be easily adapted to m squared over n squared. Okay. They grow already only as log s, so it would be some finite value, because it's a power series in m over n. But you can calculate it either in epsilon expansion or to second order in m squared over n squared and see what it is. It will also be interesting if you can find maybe the anomalous dimension of the scalar operator in m over n becomes negative. So maybe there's some heuristic argument that for a given value of m over n, the CFT would violate unitarity bound by just extrapolating, and maybe that's another way of deriving this limit. Mm-hmm. But you can't rule out that they diverge at this finite value of m over n either way, because...
But the M over N is small, shouldn't you? M over N perturbation theory valid at M over N equal to 0.1?
Valid up to, but it's never valid for a finite value. If there's a...
Mm-hmm.
But it's true that you can estimate it that way.
Mm-hmm.
Let me ask you, how much this all consideration is sensitive to a type of a tensor that are considered? So when indices take equal number of values, you can symmetrize, anti-symmetrize, so on. So is it essential or not?
I think, some people showed that recently, not too long ago, that if you were to consider, say, a single ON gauge group in a symmetric traceless representation, you would still get melonic dominance, although the subleading corrections are less suppressed. But if you do get melonic dominance, then at least the scaling dimensions of bilinears are the same. So in many respects, the spectrum in this strongly interacting thing is the same if you get melonic dominance.
Okay.
But yeah, that's...
So in this bifundamental theory of scalars, in there, that's a concrete case where you might take this limit we discussed earlier, where m scales like some square root n or some power less than 1, because you said you have a finite, you have a regime where the coupling is still real,
and then you can see if that, and you can just check if they're a real fixed point or not. A separate thing is, can you sum the diagrams? And a separate thing is, but it's true, this is a concrete context in which you can do that, yes.
Yeah, sum the diagram in the sense that m over n is going to 0, so you can keep the leading term in m over n. You have to probably be a little careful in which operators you keep, because there will be some double trace operators of one which will be like the single trace operators of the other.
Yes. I think that's interesting. And yeah, it can be made concrete in a variety of models like what I discussed.
And really, is it possible, since m over n, your critical value of m over n is small, in that case 0.1, is it possible to look at the vicinity of this transition a little bit, maybe see whether it's a third order? I mean, what exactly happens?
It's just you have a quadratic equation, okay, with the parameter, and as you change the parameter from below 0.1 to minus 0.1, the solution, it's just the parabola goes above the, and you're solving it becomes complex.
Right.
So, I mean, in the parameter alpha, you're saying, is it a...
Yeah, I mean, it's there are large n phase transitions. I mean, like the Gross-Witten-Wadia type transition. So whether this is in that same class or not.
No, I think it's probably simpler in a sense. It's not. It's just maybe there's some new marginal operator comes in, or something like this. But yeah, that can be That's.
Further questions? Let's thank Shiroman again. So we break for tea.